I want to show you something on GeoGebra. This is a great web-based geometry application if you have never seen it before. I've got a quadrilateral here, A, B, C, D. I've got this random point E in the middle, but that's not super important right now. And then I've got this slider here, and you might not have noticed, but there's something else on the picture. And I want you to just take a look and say, how would you describe the relationship of that fixed object, a fixed quadrilateral, and this variable one? You might say that I'm taking that fixed one and I'm shrinking it when the slider has a small value, and I'm blowing it up when it has a big value. I'm dilating it is a little bit more technical, or contracting it. You might also notice a lot of people would say, hey, I'm creating out of ABCD, I'm creating this other object that has the same shape but a different size. And that's exactly the notion, the big notion for this chapter and for really the next couple of chapters that we're going to be using, which is similarity. What we say technically is that these shapes are similar to each other, and that encompasses all the things I just said about dilating, shrinking, stretching, same shape but different size, that kind of thing. So let's look, I'm going to look at another thing. This is something where you guys are kind of modern generation. You have a very intimate knowledge of this from a lot of web-based applications. For example, if you're on Google Maps or something, or any mapping application, or something where you're going into zooming into and out of a picture or something like that, you're very, very used to zooming in and out. You even have this very tactile version of it where you can put your fingers on something and you can just magically make that appear to contract. You're zooming out, or to expand because you're zooming in. And again, you're not changing any shape. You are just changing the size of all the shapes on that picture. And that is great intuition. So that you're a little bit ahead of people who haven't had that experience of being able to zoom in and out of every kind of picture you ever see, pretty much. So let's look at how we talk about this. So we're talking about similar shapes. We're going to focus on polygons. It's really similar any kind of shape. Circles, weird blobs on maps, pictures of your dog, whatever. But we're going to, of course, focus on things that we're more familiar with, so similar polygons. So I just showed you how a really good way to think about that is this active transformational idea that you can take any figure, like a polygon, and you can stretch it or shrink it. You're going to, of course, produce something with a different size, because that's the point, but you're not trying to distort it. You're supposed to have the same shape. And zooming in and out of a picture or a map or anything like that is a really good metaphor, and it's exactly what happens. When you put your fingers on a screen of a phone or a touch screen, it's doing exactly the calculations to produce that zoom that we're going to be talking about. It has to know how to do this math to do exactly that. So what does this same shape imply? What does that mean? How would we detect that? How would we detect if it wasn't accurate? Well, one thing you can notice is if we go back to our algebra picture, or sorry, our GeoGebra picture, is that the angles are all the same, right? So that angle at D, which is I'm thinking of as my original figure, and then this modified one that I'm going to say is a similar figure, that angle at D is going to be the same. If that was changing as I move the slider, if that angle was changing, I would not think that I'm just changing the size. I would think that I'm changing the shape. These guys are pretty close to right angles. I don't know if I made them perfect, but if I say I want to say these are the same shape quadrilateral with different size, I don't want to change those angles. So all those angles, corresponding angles, should be congruent. That should sound a lot like congruent polygons. But of course, congruent polygons, the angles are the same and the side lengths are the same, and that's definitely not what we want here. We want to be able to change the side lengths to make the overall scale bigger or smaller. So back to here, we want the same angles, or the fancy name that, of course, we use for that in geometry is they're congruent angles. But we don't want the sides of the original and the scaled copy to be the same. But we do want, there's still something we want to be true, excuse me, that the ratio of the sides should be the same. So let me go back to the picture. So I had it calculate, let's see, I think it happened to be called F here. My original quantity, my original figure I calculated, this is BC, big B to big C, and it's calling it little b, and it had side length 7.32. And then the vertical side over here, it happened to call it A1 for its own reasons, 3.12. And I had to just calculate the ratio of those two. That's F over here. That's 2.35. And so it's got a certain ratio of width to height. You could call that what's called an aspect ratio. So it's substantially wider than it is tall. And if I want to make a new copy of this thing, I should keep that ratio exactly the same. If I move this slider and it became taller than it was wide, instead of wider than it is tall, you'd be saying, that's not the same shape. You're changing much more than the overall scale. Okay, so that's one of the things that we're going to detect a lot, and we're going to require for similarity, is that the ratio, so for example, the ratio of B prime here, 11.71, to A prime, 4.99, that's the new copies of the bottom and the left-hand side. That better be that same 2.35, and that's what I have it calculating as E here. So the A prime and the B prime, those individual numbers are totally changing. You can see those change as I scale, but if you look at E, it is not changing at all. It's still at 2.35. So that's one of the things that had better be the same. So that's a ratio, an internal ratio of side lengths, which is some sort of thing that talks about the shape that this polygon has. That had better be the same in this case. Okay, we have a name for that. That's what the previous video was about, videos. And this is really the big reason why we study proportions in geometry class. It's that the ratios of sides, and let's say corresponding sides, and we have to be careful about that. The ratios of corresponding sides must be equal. Hey, that's what we call, this is a proportion. So we say that corresponding sides must be proportional. Okay, so for example, there we had BC over AB. That was that 2.35 of the original figure. That had to be B prime C prime over A prime B prime. So the primes are nice that they just talk about the corresponding vertices of the new scaled polygon. And that is one of the shape ratios. And that happens to be 2.35 in that example. And so this is one of the ways we can think about proportions coming in for similar figures, that you look at one of the figures and you look at a ratio of two of the sides within that figure, and you get some interesting number that talks about whether it's fat, skinny, tall, whatever. And then you look at the corresponding exact ratio for the thing you're hoping is going to be similar, and that better be the same exact number, right? So that's, we could call that sort of equality of shape ratio. And there's going to be lots of ratios we could do. I didn't put it on the figure, but we could look at like the CD to BC ratio or the CD to AB ratio. All those are going to give us certain numbers that are characteristic of this polygon. They better be the same when I scale it up or down. Now, there's another ratio that's really crucial, and this is an aspect of how when you have one proportion, you can create a lot of other equivalent proportions out of it, and that is focusing on the number that's coming out of the slider. Right? If you notice, you might not have noticed it, but there's a number attached to the slider. When the number is 1, I'm not scaling it at all. I'm just reproducing the same figure. When the number is 0.5, I'm scaling it down to be exactly, so the sides are exactly a half length of what they were. Interesting thing that we'll get back to later is the area of the smaller polygon a half the area of the bigger one? We'll save that for a while, but that's an interesting question already. If that's like 0.2, then I'm scaling down all the sides by a factor of 0.2, in other words, 1/5, so 1/5 is big. When that number is 2, all the sides are twice as big, and I've got it set up to I can go like 5 times as big, but then it goes off the screen. Okay, so this is what we call the scale factor. So let's set that to be, let's set that to be 2 to be simple, right? Okay, and notice 7.32 scaled up by 2 is 14.64, 3.12 doubled 6.24, right? And I'm making sure I'm having the GeoGebra do a little algebra over here and actually double checking that for me. Suppose I didn't know that I was purposely creating the big figure so that B prime C prime is double of BC. Somebody did this, and I want to know, is this actually working? Is this what I wanted? And I just would calculate the ratio. What's this side length, B prime C prime, over BC? I noticed, oh, that's 2. Okay, that's great. But then I should check the other ratios. If I'm doing this wrong, I might have something where B prime C prime is twice BC, and maybe I didn't scale up this vertical side by the same factor. I would definitely be changing the shape. And in fact, because it knows how to do this correctly, the ratio 6.24 over 3.12, that's also 2. And so that's these ratios that it's calling G and H. And those are exactly 2, and those match the overall scale factor that I asked it to create the figure with. So that's another thing we can do. And notice it's really just manipulating this proportion here. I can look at the scale factor. If I have 2 shapes that I think are going to be similar, I should calculate the scale factor between every single pair of corresponding sides, and I better get the same number. So that's going to be, for example, B prime C prime over BC. And it should also be the same number as A prime B prime over AB. In this case, for the setting I just showed you, that was equal to 2. That's what the slider is giving us. And that's really crucial. Now, notice that these are totally mathematically equivalent. This isn't really new information. If this proportion is true, then from what we know about manipulating proportions, that's got to be true as well. Notice one way to be sure of that is I can always clear the fraction. BC times A prime B prime equals AB times B prime C prime. That's the equivalent form multiplied out, and this has exactly the same equivalent form. If I just cross multiply, I get AB times B prime C prime. It just shows up in a different order, equals BC times A prime B prime. Yeah, so all 4 of these are just equivalent statements. But there's a really important intuition that's different that you get here that's really useful. And this says you can check whether 2 figures are similar, 2 polygons are similar, by looking at all the shape ratios within a figure and making sure that they match between the 2 figures. And this says look at all the corresponding sides from one figure to another and make sure that you're going to get measurements of the scale factor you used. You better get a consistent scale factor for everything. All right, that's plenty long, but I wanted to give you all of those ideas.